Okay, welcome. My name's Gavin Nielsen, and we're going to do the second session of our introduction to modeling, simulation, and analysis. This is the kind of the first official, but the second step into MATLAB language fundamentals. The first session said don't panic, and now it's time to panic. We're going to get into some great stuff today, so thank you for coming or listening. Another title for today's lecture is How Far Down the Rabbit Hole Goes. And if you don't understand what that means now, just wait. If you don't understand what it means when we're done, I'll mention something about it. Another title for today's lecture or seminar is To Infinity and Beyond. Yes, I realize that's a Toy Story quote, and I'm not ashamed of that. Again, you'll understand what it means as we move along here. But I think it's good to have more than one type of quote or more than one type of title for things. Just adds a little flavor. All right, so the agenda for today. We're going to cruise through things like we did before. We're going to learn some new modeling concepts. We're going to talk about vectors, abstractions, and interfaces. And there's a few new language concepts we're going to learn, not very much, just a few new things. Mainly we're going to learn about functions. And then we're going to spend just about 5 minutes and go from a single bouncing ball to n bouncing balls, just to modify last week's project so that we can sort of elaborate a little bit. And then we're going to do a really cool challenge, and that's to model a piano. And so what that means is to interpret a set of notes as frequencies and durations, adjust the attack of those notes. And I have Play the Star Spangled Banner. We'll see what we feel like when we get there, but we can play any song we want. So that's the idea. So without further ado, let's get into it. So a vector has a few different definitions, and I'll just skip right to it. The one that we're going to be talking about is one of the more general, and it's a matrix with one row or one column. So if I break that down a little bit, we can think of that as if we had a zero-dimensional variable or a scalar variable before, we're just taking that to the next step and saying a variable with more than one value, but it just has one dimension, so it's just a string, a sequence. Next, it's our first higher dimensional object, and we're going to see some interesting higher dimensional effects come into play, which is kind of fun. And that higher dimension, it has to do with the fact that there's no technical limit on how big the vector can be. So there's practical limits just for computing that, okay, well, we can't have a vector more than, I don't know what the limit would be, maybe it's 200 million elements or something like that, but in theory, it's arbitrarily large. And for most practical uses, it's arbitrarily large too. For a lot of things, we don't need to get up to 2 billion elements. We can do amazing things at 2 million or 200,000 or 2,000. So that's what a practical vector is. So what can we use them for? Well, we've already seen them actually in our data capture from last time. Remember, we captured the path of the bouncing ball. We were building a vector one by one. And we can use them also for an ordered sequence of incrementing values, like time or space. So if we were talking about a time vector, we're talking about, maybe it's one step. The step is 1 second, so you go 0, 1, 2, 3, 4, and there's a vector that has all those time steps. It could be an ordered set of coordinates. A little foreshadowing here. Right, we only had one coordinate because we're only tracking one ball. But how do you think we're going to be able to track n, like Nancy, different balls? Well, we're going to do that with vectors because we can create an ordered set of coordinates doing that. In a nutshell, it's anything we want to use all the same type, or I should say type same, whatever, elements in kind of a uniform way. And I say this in quotes because if you really wanted to, they really just have to be the same type and you can use them however you want. most efficient use in MATLAB is really to think about using them in kind of a uniform way. And we'll see why that is. So why should I care about vectors? And this is very important. If you don't care, I hope we can convince each other why they're useful and why we need them. So first of all, they make writing descriptions faster. And again, time is the enemy. We're trying to figure out how we can model things, simulate them, and analyze them as quickly as possible. So we want to make, however we describe the model, we want to make it faster. It's also easier to read. We'll see how we can actually condense things and make them more clear, more concise by using a vector type notation. They allow for dynamic sizing, and that's sort of like our bouncing ball demo. We have one ball now, but we're going to change it so it's based on a variable, and that variable could be 2 or 1 or 20,000, doesn't matter. We can dynamically size things, and we can write algorithms that handle any size that comes through. And they're great at capturing patterns, and I mean this kind of literally and figuratively. Like, for example, with our bouncing ball demo, we were capturing the path, which was the pattern of where the ball had been. But different vectors, like a amplitude vector that you might capture from a data acquisition system. Anyway, it holds those patterns in a structure. And then maybe obviously, maybe not obviously, they're used extensively in mathematical descriptions of phenomena. So when you go model something, 9 times out of 10, someone else is going to know more about it than you do. So you're going to need to go read and see what everyone else has understood about it. And so vectors are used all over the place in mathematical descriptions because of the fact that they're so efficient and so useful and make things clearer. So in order for you to read what people already know about stuff, you're going to want to understand vectors. So here's a vector field, and this is showing sets. This is a set of vectors. So each one of these vectors has a position and it has an orientation. And we can learn a lot from this vector field because you could think of this as like a cross section of a whirlpool in some rapids, like some very violent river, and it has these little whirlpools in it. Well, this vector field, we can at a glance understand what's going on and maybe have an idea how, if a particle was started or initiated, positioned in a particular place, where it might travel to based on the vector field. So that's another example of being able to capture patterns. This is not a single value kind of a thing. This is a complex thing, but looking at vector fields and using vectors in general allows us to express them easily. So just a few more examples of vectors just to get your feet on the ground. And another way of saying a vector is a one-dimensional array. That's the way we're going to be using them today for the most part. But a coordinate in 2 dimensions is a vector. So like x, y, let's say those values are 3 and 4. X equals 3, y equals 4. And that's the distance from the origin, right? Well, that's a vector, actually. The output, quote-unquote, path from our ball was a vector, and that had a sequence of values that represented all the past values of the position over time. If you think about our piano example coming up, we could think about the sequence of keys we press on the keyboard as a vector, or the instant that we pressed them, those time instants. Maybe that's the vector we want. Or maybe we're just talking about a set of numbers. Maybe it's the integers from 1 to 1,000, and we want to put them all in one variable. Maybe that's our vector. So lots of vectors are very flexible, and we can't enumerate all the ways and examples we can use them because they're just all over the place. So we'll keep rolling, and you'll get used to them. Okay, so it's time. We need to get back to the real thing. We need to get a little dirty here. So let's hop over to MATLAB and do some vectors. So Let's start with creating a variable, and we'll say it's 1 to 100. I'm going to hold down Control and press Enter, and I want you to notice what happened in the command window. It added all of these different columns. We didn't put a semicolon on the end, so it echoed it all to the command window. So I'm going to type CLC to clean that up. You'll also notice it created a variable named T, and its size is 1 row, 100 columns, and it's a type double, which we'll talk about what the type double means another time. But basically it's a real number. So we just, in one line here, created a variable that has 100 values. Super efficient, right? What if, so this steps, so if we remember, we can ask for indices of this thing. So if I said I want to know what the first index, or array position 1 has in it, it has 1 in it. And maybe array position 2, array position 44. Okay, well, this is great, but maybe we don't want to step by 1. In other words, maybe we want t equals 1 to be 0, or sorry, t index 1 to be 0, and the next time step, maybe it's smaller than that. Maybe it's 0.1. What we do then, you can see up here, and I'll put a semicolon at the end of this, is we pick the starting point, I'll make it 0, then we put a colon, and then we add the step, in this case 0.1, and then we add the ending position, which is 100. So I'm going to hold down Control and press Enter, and I'll clear the screen here. You'll notice that t is now 1 by 1001, and that makes sense, right? Because for every 1 we have 10 values, and we go to 100, so there's 1000, and there's an extra 1 because we started at 0 instead of 0.1. So that makes sense, and we can, so this is super useful. So we learned a couple of quick things here. We used the new colon operator, which allows us to create variables very easily and quickly. Now, what if, so I'm going to create something that has a slightly smaller step, and we're just going to go to 10. Now, sometimes you want to operate on a variable. Let's say that you want to feed in the times, and you want your output to be the sign of those times. So I'm going to Control Enter here. Now we look here at the bottom in the workspace, and now it has variable y, which is exactly the same size, 1 by 1001. So we passed it a variable that had 1001 elements in it, and that created a new variable y that had a matching 1001 elements. So if we want to see what that looks like, of course we'll use plot. T on the x-axis, y on the y-axis, hit enter. Sure enough, there it is. And we can, if we would like to see all the points that has, we can change to the dot dash style and zoom in a little bit, and we'll be able to see these points. So you can see it's created a sequence of these points, and in 3 lines we created over 1,000 elements in one vector, and then we calculated 1,000 or so elements in another vector, and we plotted 1,000 different points. So very, very useful. Okay. It's key to remember that when you pass in something like this, you pass in the variable t to the function. Most of the time, depends on the function, but it's going to return a variable that has the same size. Okay. Alright, so let's get back to the lecture here. So we're going to talk about abstractions and interfaces. So we'll start with the definition. That's good place to begin. Abstraction. I think I'll just skip to number 4, the process of considering something independently of its associations, attributes, or concrete accompaniments. And when you read that, I hope something goes off in your mind and you say, man, that sounds really similar to models. Well, that's because it is. It is very similar. And we'll talk about the difference. A model is, just to be frank, a model is an abstraction of the thing it's modeling. But I want to point out some differences. So that's the definition of abstraction. Now, interface, looking at definition 1, a point where two systems, subjects, organizations, etc. meet and interact. And I also like the physics definition here. A surface forming a common boundary between two portions of matter and space, e.g. between two admissible liquids. So think about the two things we have here. An abstraction is considering something independently of its associations. It's kind of the idea of separating things. You're abstracting something from something else. So you're creating a division. An interface is the point where two systems or two things interact. So they kind of go hand in hand, which is why I wanted to define them. I wanted to define them together. So practically, what does this mean in our context in modeling? An abstraction. Okay, like I said, we must use an abstraction from the object we're modeling. That's what separates the source from the projection or the approximation. Now, we create a new idea or notion that is an abstraction of the thing we're modeling, the source. This new notion becomes our model. So that's one way to think about it. Again, I don't want to focus too much on the philosophy. The more important thing for our discussion today is talking about abstraction layers. And we add abstraction layers or layers to our model for two reasons. One is we might be mimicking layers that we see. Like, for example, maybe you have a computer that you're modeling, and maybe the computer has a motherboard and then it has a video card. Maybe it has two video cards in it. So you might mimic those layers and create models that have the same layers that match the thing that you're modeling because you're mimicking it. On the other hand, there might be something that's a very complex process, and you might create synthetic layers. So you might add a layer. Maybe I'm talking about, like we'll talk about our piano problem later, and we might have layers that don't actually exist in the real world, like needing to look up the frequencies of a particular string or key. But it's a very complex process. So for us, we're adding it to simplify the modeling process. So sometimes it's to add accuracy, and sometimes it's to make it simpler or easier. So interface. What's the practical idea of an interface? As we model, we create a system of layers or abstractions. Each layer has interfaces as needed. So we define where the abstractions are, and we define where the interfaces are. And those interfaces is how the layers talk. That's how they communicate. So as you're designing your model, you create your abstractions and your interfaces in such a way that everything flows and it makes sense for whatever you're doing. So now kind of digging into interfaces and abstractions a bit. Most interfaces have either inputs, outputs, or both, but they have to be defined at the transition. Remember, interfaces exist at the boundary, and they become part of the vocabulary of the interface. And we'll talk about in just one slide or so what I mean by part of the vocabulary. So a couple examples first, though, just so you get this in your head. Okay, if we think about the U.S. nuclear chain of command, the final guy who actually launches some nuclear missile is, I don't know what the rank would be, but he's definitely a lot lower than a general, right? But there's a lot of people above him in the chain of command, and the person that we put in position to make the decision of whether we're going to launch a nuclear strike is the president, right? He's at the top of the list here. Well, the president is, that office is an abstraction of the authority, right? And there's a layer underneath him. That office of authority is the Secretary of Defense, and that Secretary of Defense, and they have an interface. They talk to each other. The President commands the Secretary of Defense. The Secretary of Defense reports back to the President. In the same way, the Secretary of Defense commands the Unified Combat Commanders, and so on and so forth, all the way down to the person who actually pulls the final trigger to launch the missile. And I like the little dotted dashed line here. It's implying that slightly above the president is the engineer who installed the red button. I just think that's kind of funny. So in this situation, we're talking about a leader, and he can't directly implement his intent. He has to delegate. So we're not trying to mimic something per se. We're trying to make the situation easier, because the president doesn't want to go talk to 10,000 or 100,000 or a million different people to implement what he wants done. And then for efficient structuring of this, it's not like the president has 20 secretaries of defense, and each secretary of defense has, a million people. We put them in ranks that make it reasonable and efficient. So we already talked about the interface bidirectionally, inputs and outputs. Okay, here's another example. The interface of a car, an abstraction layer. It's easy and natural for us to think about the steering wheel as an interface. When you think of an interface, you probably think about software, actually. And since most cars are fly-by-wire, steering wheel probably jumps to your mind as an interface, but it's also an abstraction. So let me explain what I mean here. So on the right-hand side is what's actually going on. When you turn the steering wheel, something along these lines are happening. If you're going straight, it looks like the upper left under the actual. If you turn left, it's changing the angle of two different tires, usually in the front, and it's solving an equation that says the axis of the tire needs to point to a place that lines up with two other lines. And I don't know if you've ever thought about this, but if that doesn't happen, then the wheels, the rubber on the wheels will rub off very quickly, and it's called scrubbing, and that ends up with very, very low tire life. So you need that to work correctly. And so that geometry and that solving of the equation of how to get the tires to the right angle is being abstracted for you, and all you have to think about is how much you'd like to turn to the left or turn to the right. Also think about all of the machinery in the upper right-hand side of this picture. Think about all the machinery of the tires, and the caster angle, and the camber angle, and the pitman arm length. And if you're interested, go look up what those things are. But there's a lot going on when you turn the wheel, when you turn the steering wheel. And so we need a way to communicate, so we turn the steering wheel. That's our interface. And we've got a lot of other buttons there in the picture. And we also need an abstraction from the complexity going on underneath. Okay, so in programming, since we're using programming as a language to do our modeling and simulation tasks, we can think about abstractions and interfaces in terms of functions. So you probably are familiar with functions from math, and you know that y equals f of x, and maybe f of x is x squared, and so y equals x squared, and you can tell me all kinds of interesting things about that, I'm sure. But programming, in a lot of ways, kind of says it doesn't have all of the rules that mathematical functions have. Kind of allows us to be a little more free in what we do, and we can basically use it to abstract whatever we want done. Even if it has more than one output, more than one input, doesn't matter. We can use functions to abstract away those details. So a simple one is a sign of x. So x is the input. Sign function abstracts details of some algorithm, and y gives us the output. That's where it stores the output. So we can define exactly the sign functions built in, but we can create a new function. There are also some functions we've been using already that don't have input or output, and that might be CLC or clear. And there's an implied set of things to do, actions, but it doesn't give you a formal output in the sense that you can store it in a variable. It just handles something for you. So it's a little more procedural, but they're still think of them as functions. Okay, so here's the concept in MATLAB. And the concept in MATLAB is that you create a new file, a new script, and you write the word function. And then if you have any outs, you list them. Or if you have just one, you can write it, put it in brackets. And then you name your function. I called it my_FCN. And then you put all the inputs you have. If you don't have any, it's just open and close paren. If you have one, then you put the name. If you have multiple, you separate them by commas. Then you have a set of commands, and when it gets to the end of the file, that's the end of the function. So that's pretty simple, and that's part of the power of MATLAB, is it keeps the simple things simple. So yeah, ins and outs can be of any size, dimension, or type, which is pretty neat. They can be scalars, vectors, matrices, 20-dimensional arrays, whatever, strings, whatever you need them to be. So, all right, and this is just a thought. When you think about a car, you have an idea of the notion of a car. Have you ever thought about how to organize it, though? How you would structurally group things? You know, maybe the tires are all instances of the same thing, but then the left door is not quite the same as the right door, so how do I think about those? And all these nuts and bolts. There's just a tremendous amount of parts in not even a late model vehicle. There's something to think about. Something to think about how many parts there are to a system and how you should organize it. So that's just a thought-provoking question. Okay, now let's do some functions. Let's get in real quick and just do some examples of functions inside MATLAB. Okay. So the first ones, we're going to do some no input, no output things. So let's try writing one called function. See that highlights there. I'm going to call it gab1, empty parens. Hello everyone. Okay, now when I save, I'm going to go up here to save. It's going to prompt me to name it the same as I called it here, which is a good idea to do. So I'm going to say save. We'll see it show up here, and you can see it's got a little fx next to the file type. So it's a script.m, but because we created a function, it's a function script. So I can call it here, just call gab1, and it does what I ask it to do. And if I say gab1 and do the open and close parens, same thing. Okay. There's another example, but I'll move on quickly. You can look at that later. All right, let's say we have multiple inputs. Here's one that has 2 inputs, and I want to show the variable that has one input times the other input and then display it. So how would you write that? So I'm going to create a new file. I'll call this one function. You have 2 and 1 and 2. Something called a show var, and it's going to be in1 times in2. I'll display show var. So I'll save this. Yes, gav2 sounds good. Now this one, if I just type gav2, it's going to say, hang on, you need to put in more arguments. There's not enough input arguments. So what we need to do here is put in gav2, 3 and 4, or whatever numbers we want, and 3 times 4 is 12. Okay. So there's another quick one. Okay, here's some output examples. Let's say we just want something that gives us a number. Okay, maybe the number is a big number, you don't want to type it in all the time. So we write something called function sn for some number. And we say, oops, we call it my num, save that. Okay, and my equals 9.45322. That sounds pretty good. And hit save. Okay, so when I call sn, it automatically knows exactly what that is. And so, in a sense, you could use a function just like you would declaring a variable, except it just gets saved in a file in a different way, and it's always available. It's kind of a neat thing. If you wanted to store the output of that, you could say x equals sn. And that puts the value into x. Okay, now what if I have multiple outputs? So we need to put them inside a bracket. So I'm going to do that one real quick. So we'll do function, number of Avogadro, and the speed of light, and we'll do sn2. We don't have any inputs for this. And we'll say number of Avogadro equals 6.002e23. And c equals 3e8. 3 times 10 to the 8th meters per second, right? So Avogadro's number and the speed of light. So we'll save this, and this will become sn2, which it defaults to. And now I can quickly say, oh, sn2. How come it only gave me 1? Well, that's because I didn't give it any place to put the other numbers. So if I wanted to catch both, I would need to put a function, or excuse me, a variable or set in front and say my NA, my C, call them whatever I want to, SN2. Okay, now I've got them. Now I can catch them, you might say, in the return. Okay, very good. We're cruising along here. Okay, so CMO and MISO, single input, multiple output. Let's do one of those real quick. This has a function, we call it perk for percentile. I'm just doing something easy here, so I'm going to actually copy and paste this in. We'll see if I did this right, huh? All right. PowerPoint converted 3 dots into a different character called an ellipsis, so I had to change that. But I think everything else is good, so I can hit save. That calls it perk. Good. Okay, let's just see what it's doing. We're taking some number, my num, and then we're returning S25, S50 and S75 as the number times 0.25, the number times 0.5, and the number times 0.75. Okay, so again, I have to catch them all. So ABC, we'll catch it as perk of about 12, 3, 6, and 9. Okay, does that make sense? We're just passing in one argument, getting out 3 arguments. this is the definition of how to say that. Alright, let's try MISO, multiple input, single output. Just create functions like a madman here. Okay. What is this thing? This is G average, Gavin average. And I'm returning something called AVG for average, and I'm passing in N1, N2, and N3, and I'm defining average as the addition of all these 3 divided by 3. Okay? So I just saved it. Let's try it. G average of 3, 6, 9. Answer 6. That makes sense. Okay. Very good. So we cruised through those function examples. All right. So we've got some vector stuff. We've got some function stuff. Now, what does all this mean? Or not? How do we? Let's talk about the language. I'm sorry. What do we need in the language? Okay. So first of all, we've already talked about colon operator. And we've used it to declare vectors using start, end, and step notation. We won't use this today, we'll use it another time, but you can also use it to specify which parts of indices. We won't get into that today. There's the dot operator, which we'll come to later, but basically means to help you specify different ways of expressing how to operate on number sets, whether you're using matrix or vector types of things, or basically linear algebra definitions or array definitions. So we'll talk about that in a little bit. We've already learned about the keyword function, and that just precedes a function definition, and you can pretty much do anything you want in a function. But we also need something else. We need the switch case otherwise structure. So I want to demonstrate what this is. This is just like it sounds like. The switch case otherwise structure. I'll do our normal clear, format compact, CLC, and let's look at this and think, what are we trying to do? So use a switch statement. Okay, and these are especially great for functions because of the fact that sometimes you handle a set of cases. But let's talk about what a switch statement is. So let's say we have a variable called x, and we make it equal to 4. And previously, if we wanted to handle 4 different ways, 4 different conditions of 4 different values of x, we might say if x equals 1, do this, and if x equals 2, do this, and if x equals 3, do this. In the do this, we could have it do something particular for what we needed. And if x equals 4, do this. Okay, so if we had, this is how we have it working right now. I should say this is the language that we have to describe this stuff right now. Switch sort of simplifies this, and instead of saying it this way, we can say switch x case 4, do something with 4. Actually, I'll start with 1 just to make this a little easier to read. Case 2, do something with 2. Case 3, do do something with 3. In case 4, do something with 4. And then we can just put end, and that's enough. But in the same way that you remember if statements, we could also add an else. Do the non-one thing. We can add an otherwise. Do stuff outside 1 to 4. So it's sort of like a switch. I mean, that's it's sort of like a mechanical switch is what I meant to say. That you plug in an X and it goes into whichever slot. It executes the code in whatever slot you it happens to be. So if X is equal to 4, then it outputs everything here. X is 4, you know. So when I run this, it will get to that case, display X is 4, and there it did it. So that's what the switch statement is. It makes a really easy way for us to make things like lookup tables and situations where otherwise it would end up being a lot of if, then, this, else, equals, and you end up saying X is this for a lot of different things. You're actually asking the computer to do a lot more processing than it needs to, because it's evaluating, is this condition true, or is it not true, or is this condition true? Okay, is this condition true? Whereas this structure allows it to evaluate X once and pick which structure of the tree it should go down. So decision trees and a lot of these sort of things. The switch case otherwise structure is super efficient. Okay, what else? Another thing, sound. So because we're going to do a piano model, we want to use the sound command. And what sound does is just sends a waveform to whatever sound subsystem you have on your computer. And so that's really useful for us, because then all we have to do is define any waveform we want, and we can send it to our sound card. And that abstracts the sound card, and it makes it a really nice interface in order to interact with the sound card, right? To use some words that we just defined. So let's look at a demo of that real quick. Alrighty. Get rid of all that stuff. So actually, let's go to doc sound. We don't demonstrate the help system enough. So it shows you can talk about, send just the waveform, send the waveform and the sampling frequency, send the waveform, the sampling frequency, and the bit depth. So here's an interesting, a little bit of example code that we can use to learn how to use this. I'm going to paste this into here and run it. Hopefully you could hear that. It loaded up a gong sound, and hopefully my microphone picked that up okay. Let's add handle real quickly. Okay, we can see that when we load handle.mat, we'll talk about the load command later, it loaded up this y. And y was a vector that was 73,000 plus a little bit of rows and one column. So 73,000 samples. And it defined the FS, or the sampling frequency, as 8192. So one of the things that they say here is try doubling the sampling rate of playback. So we'll just do that to make them happy, but it's also kind of interesting. Okay, if you could hear that, hopefully you can. What that did was it was playing back the same waveform twice as fast. So it sounds like it sped it up or compressed it. Actually, what it was doing was just interpreting it differently and saying, okay, well, if this is how fast that your sampling rate is, that's how fast I'll read the values. So if we, by the same token, if we do this, oops, that's half. Wait, that's pretty bad. Let's go 80%. I can't take it. Oh, I forgot. For reasons we'll discuss in a little while, we have to wait for this to end. Okay, I'm going to make it 0.8. Okay, that's enough of that. But the sound command is great because it allows us to audibly hear our data, our vectors that we're going to create. Alright, now these three, zeros, ones, and rand, are sort of useful constants for working with vectors and matrices. So what they are is, if I was defining a scalar variable, I could just say x equals 0, right? But what if I want scalar? What if I want x2 to be a zeroed vector, where they're all the same? How do I do that? Well, use the zeros. Maybe I want it to be 35 long, 35 rows, 1 column. Okay, now if I run this, and then I put in x here, or excuse me, x2, I can look and see, okay, I have a vector that's all zeros and it's 35 by 1. You can see its size up here. Okay, very good. That's zeros. And ones is exactly the same idea. So this time we'll make x3 equal to ones, and this time we'll give it 1 row and 35 columns. I'll leave off the semicolon so we can watch it. Okay, columns 1 through 35 displayed, and they're all ones. And it's super helpful because maybe you want them all to be 7. That's alright, just say 7 times ones. And there you go, they're all 7. So that's also helpful when you're working with vectors to initialize and what's it called? Can't think of the name, but anyway, pull them into memory all at once instead of adding one little by little by little, the way we did for our path vector for the bouncing ball. Okay, the third one here I wanted to point out is random numbers, rand. So now let me demonstrate this a little bit. If I just say rand, it'll give me a random number. So I can say rand over and over and over. You'll notice none of these are coming back the same. But what you will notice is they're all between 0 and 1. Okay? So if I say rand 3 by 1, 3 rows, one column, it'll give me 3 random numbers. Or maybe 3, 1 by 4. 1 row, 4 columns. It gives me 4 random numbers. So when you just want to get something going, you don't want to pick the numbers yourself, you can make the function call to rand, and whether it's a scalar or a vector, it will return numbers that'll fill those, and it kind of gives you a random seed that you can, it's technically pseudo-random, but that's definitely beyond the scope of what we're talking about. So that you can go and have some different, first initializations. It's useful. It also helps you try different parameters in a particular range. So that's rand. Okay, those are all the language items. So now we'll move to the ball, multiplicity of balls. Okay, so what would it take to make an arbitrary number of balls using the algorithm we already have? Alright, so we're basically going to introduce vectors into that algorithm really quickly. Now, let's close some of this stuff. And I'm going to go back to where I stored that, which was back here. I called it ball 1. So I'll copy that. And I'll go back to day 2 and put it in here. Okay, notice how it has a different, it has a little MATLAB symbol in a script instead of the fx, because this is a script, not a function. Alright, so we'll open that up. Hopefully this looks familiar. This is exactly the thing that we did last week. Alright, so just to remind you of what this is, I'll hit run. That's pretty cool. Okay. Alrighty, so since that's not going to end, I'm going to kill it, Control C. Alright, so now I have this, and I want to save it as a new thing, because I don't have one ball, I have n balls, so I'm going to call it ball n. Alt, oops. So I pressed Alt F A for file save as. I'm going to rename it ball n, say OK. Alright, so what do I have to do to go from one ball to n balls? So the first thing is I'm going to define n, and I'm going to make n2 to start with. Okay, so we're starting it out at 0, but I don't have just one ball anymore, I have n balls, so I'm going to make this zeros 2 by 1. Oops, n by 1, right? I'm going to make the position a set of zeros n by 1. Okay, now stick with me here. I don't want all the velocities and all of the positions to be the same, because then we're going to watch all of the bouncing balls bouncing together right on top of each other. You'd only actually see one. So here I'm going to use the rand function, and I'm going to use it multiplied by 20 and 35. So I'm going to say 20 times rand n by 1. 35 times rand n by 1. Gravity, it's still just gravity. Okay, all this stuff's okay. Okay, now you remember that path x and path y are already vectors, so I don't want to deal with the complexity of a vector of vectors, which is a matrix right now. So I'm going to leave this off. I'm just going to comment it out. It'll get too messy to look at anyway. And I'm going to leave this just like it is. All this stuff is okay. Okay, now the only thing we really have to change is these collisions. And we'll get rid of the paths because, again, they were already vectors. If we make a vector of vectors, they'll become matrices, and I don't want to deal with them right now to be quick. So I will say we have the while command, which we could use, but I'm going to introduce you to something really quick without explaining very much, and we'll talk more about it next session. So we'll talk about this session 3, but the for loop. So this is another kind of loop that I'm going to use the variable I equals 1 to n. And so I'll explain more about what this does, but it's a faster and clearer way to execute this particular loop. And I'll end it there. Then I'll highlight this and indent it so it's easier to see what's going on. Okay. Okay. Now, what this is saying is iterate this loop, and every time you go through the loop, change the value of I. The first loop it has I equals 1, the second loop I equals 2, I equals 3, all the way until I is equal to n, which we defined above. So we need to make these collision decisions based on if that particular ball is greater than, the position of that particular ball is greater than or equal to 20. So what we're going to do is add the index I to this. And basically all of the things that refer to vectors, we'll convert them so that they're not, the expression is only talking about one indexed piece of the vector. It's almost a brainless thing to do, but as you're getting used to it, I'll go a little bit quicker on this one, and we'll talk in a lot more detail next week about this. So don't worry about it if you're not following what I'm doing. We will come back to it. This is just an idea to show you how easy the conversion is, and we will get into more depth. I'm just adding all these subscript i's to the places it needs it. And the places it needs it are within this block on all the things that have now become vectors. Position y is a vector. And velocity is a vector. Okay. All right. I believe that will work. So, how many do we have again? N equals 2. That's enough. Let's just try that. Uh-oh. What's wrong here? It says, made a mistake here. It says the index exceeds the matrix dimension in line 36. So we'll click on that and go to line 36. So 36 has position y. We must not have must have accidentally set position y to something that was not. Okay. This will highlight all the position y's. So there we set it to zeros. There we plotted it. Here we updated it, but these are all vectors now, so this should be fine. Found the first one, so it might have been down here. Aha! I missed one, right there. So it reassigned position y to a scalar value, and then the next time through it said, hey, you're not a vector anymore. And that collision because we did have two balls here working. Okay. So this is pretty cool, right? Now we've got two bouncing balls that are in different positions, and it looks like they're just happily bouncing away. All right, but let's not be happy with two. We got to crank this up a little bit, see if we're as good as we think we are. So let's try 5. That's cool. Still not enough. How about, let's double it. 10. I'm kind of curious to know where the computer will actually have some problems. So let's keep doubling this. That's 10. How about 20? Still no problem. Interesting how our algorithm still works, right? That means we worked hard on it and did a good job. How about 40? Okay, how about 200? That's pretty cool. Alrighty. So I'm going to make a little bit of a change here. Instead of being 15 big, I'm going to make these size 10, just because with all the dots, it's going to get crowded. How about 2,000 balls? That's pretty cool. You can imagine doing some kind of molecular, obviously 2,000 is a pretty small number of molecules, but I wonder how many of the effects you could approximate. Like, for example, all these collisions could be creating forces that could be creating a pressure on all these walls. Maybe you could do a little simulation to simulate the pressure on some non-uniform surface of some kind with this kind of a simulation. That would be kind of interesting. Okay, so I want to see, when can I get this to crash? How about 20,000 balls? Oh, wow, still pretty solid. Now it's starting to look more like water particles. Okay. I'm going to start them just, we'll just leave it 0, 0. How about 200,000? That's 20,000. Wow, I don't think we're quite at 24 frames anymore, but that's cool. That is 20,000 unique balls colliding on 4 walls. And we're looking at the sum total of all that. And it seems like we're gaining energy because it looks like the balls are moving faster. Speaking of which, I wanted to point out something. We talked about last time that it seems like we don't conserve energy in the system. And I wanted to point out one of the issues that I had thought of since last time was that in our simulation, we update our acceleration with gravity right before we detect and reverse with collisions, which means that every collision will have some acceleration in it. So if you stop and think about that for a second, really you should accelerate after the collision so that the collision itself has the same amount of energy going in and going out, so you don't add more energy. I think there is still, if we wanted to get more technical in this, we could dip further into that, see how far that rabbit hole goes, but I think that's enough for this topic. All right. So let's close this. So we did a great job here with ball N. So now the new project. Okay, this is the exciting thing. So you look at the piano. It has 88 keys and complex mechanisms for hammers and strings and tensioners and resonant chambers, all kinds of different things. How are we going to model this thing? Obviously, we're not trying to model the three-dimensional structure of it right now. We're just looking at trying to model how this is actually represented. So, what's another way? Let's talk about the issues here. So, my function definition here is the result is model, simulate, and analyze the piano. Just to remind you of MATLAB function syntax. Okay, so this does sound ambitious, right? And the no is a question mark. Like, this does sound ambitious, no? So what are the requirements? What research do we need to know about pianos in order to model them? Seems like we might need to know a lot. And what fidelity or how faithful are we trying to be when it comes to modeling the piano? Because there's so many subtleties. Is this going to be super rough? Is this going to be really detailed? Are we just trying to make some kind of noise because they make a noise? And then lastly, and maybe most importantly, what's the purpose of this exercise? In other words, what does the model do, or what is being simulated? This is a really getting at the details or requirements for the modeling exercise. It's a good opportunity just to say, hey, okay, what is the model, the purpose of the model? Okay, so let's answer some of these questions. So, from our point of view, pianos map key presses to musical notes, and notes are finite length waves. Okay, so a note is not a scalar value. A note is a sequence of scalar values, vectors, but they're finite length because a note doesn't go on forever. Okay, how faithful are we trying to be? We only need the primary frequency of the note, because there's actually a lot of frequencies that's in the note, but for our first order model, we just want the primary one. We want the duration to hold that note down, and we want some attack-release dynamics so that things don't sound clippy and clicky. Okay, what's the purpose of this? Okay, we want to create a simulation that can play a song. So we want to be able to write in a reasonably simple way a little song that our simulation can play. So that's what we're after. Okay, so where do we start on this thing? That's sometimes the hardest question. You know, one of the hardest questions is why? What's the purpose? What are the requirements? Who cares? Is it going to make us any money? You know, these are some of the important questions. But once you kind of have your keel in the water and you're trying to, figure out, how to go slay the dragon, just to mix as many analogies as possible, you've got to figure out where to point the nose of the boat. Where do we start? How do we get going? All right, so first, let's talk about what a musical note is. So it's a particular frequency held for a particular duration with a particular attack. And I think frequency, most people understand what a frequency is. It's frequency is a measurement of periodic motion. So like maybe your wheel, if you're, what's a good example? We can hear things. Oh, I know a good example. When we watch movies in the theaters, they're usually shot at 24 frames per second. That's a frequency. Frequency at which a new frame is put in front of your eyes. And if they slow that down, once it gets below, I think it's like 13 or 12 or somewhere in there, you can start to see the individual frames. And when they get higher than that, different psychological things happen, like I think they went to 48 hertz on one of the Hobbit movies recently, and that had a different psychological effect. So anyway, that's what frequency is. It's how fast you put something up, like cycles per second or rotations per minute or miles per hour is a certain kind of frequency. But we're talking about sort of the, yeah, well, let's not get into that. All right, so how can we define this thing that's oscillating? And sine function is something that we've, is a great mathematical model for this because it's oscillator. It's an oscillating function. So what we need to do is we need to take and create a time vector, which I showed an example of. T goes from 0 with steps of 0.01 up to 10. And then y, which is going to be our output or our displacement variable, is sine of t. Okay, so let's just try this real quick. So let's hit escape, go over to MATLAB. Let's do this real quick. Clear, compact, CLC. I'm going to call this play 1. I'm going to call it test 1 actually. So we're going to test some of these things and make sure we've got a good idea of how to do them. 0.01 to 10, y equals sine of t. And then we want to see if that looks right, so let's plot it, t and y. Alright, let's run this. Okay, so here is our oscillator. This thing is moving back and forth. And you can see that one peak is around 1.8, and the next one's around 7.9 or so. So this is a pretty low frequency, and we actually need to bump this up a bit. But you get the idea of how we can represent. So what we did here, if you look at the workspace, we had made two basically 1,000 element long vectors, one for time, one for y, which is the displacement vector, and we used time to define what was going on here. Now, I want to talk for a second about frequency. So if I say my frequency is 1, and I put in here f times t, then it stands to reason I'm going to get exactly the same thing, right? Okay. I'm going to put a semicolon so it doesn't keep spitting out numbers. But what if I said f is 1.5? Now pay attention to what's going on here with this wave. Okay, these are getting closer together, right? What if I make it 1.8? What if I make it 2.5? So as my frequency increases, those oscillations are getting faster. Okay? All right, there's one other thing I want to point out. If, let's just say I wanted this to be 2. But you might notice, let's start at 1. Okay. When we look at this here, I'm going to put a data tip on here and get it real close to 0. Okay. So here's one cycle. Now I thought I was doing frequency of 1. Well, here's the thing. The sine function, you might remember, let's just do the doc on that, doc sine. The sine function takes in the argument in radians, not in cycles per second. So if I was giving it the definition, if I was giving it the parameter, the input, in terms of cycles per second, in terms of hertz, then this should finish 1 at 1, because it's doing 1 cycle for 1 second. These are supposed to be seconds. So we actually have to convert this and add a scale factor of 2 times pi. And pi, so pi is 3.14, blah, 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 goes on forever. So 2 pi is the number of radians there are in one cycle. So there's 2 pi radiuses in each circumference of a circle, just in the same way there's 2 pi radians in one cycle of a sine wave. So now, if I do the same thing and hit go, and I'm just going to go from 0 to 3 now, I can see it actually does finish where I expect it to. Okay, so that's an important thing. We just need to convert from radians per second to cycles per second. All right. So what's next? Okay, so digital audio has a sampling rate. You may have heard some of these terms before, and we're going to talk about them briefly, and you can go look them up if you want to go into more detail yourself. But if you think about it, we have to evaluate individual points. And those individual points have a certain step, or a certain resolution, or implied in it. If you think about going and measuring, like recording audio, you're actually recording a pressure at a certain speed. So there's the frequency, I don't want you to get confused, there's 2 frequencies we're talking about. There's the frequency that the sine wave is oscillating at. So if we run this again, I'm going to run it, but this time I'm going to include dot dash after it. Whoops. What did I forget? Sine. Oh. Should have been in the plot command, not in the sine command. There we go. Okay. So there's 2 things I want to, there's one thing I want to point out here. Zoom horizontally. Alright. So there's one cycle from 0 to 1 here, right? But you'll notice this is composed of all these little points. So during that one cycle, we captured a certain number of points. In fact, we captured 100 points because we said we want to take a step of 1/100th, 0.01. So those points are actually the sampling frequency. Now the sampling frequency we can define up here and say Fs equals 100 samples per second. And then the time sampling amount is 1 over Fs, 1 over 100, 0.01. So then we can just put in here Ts, and this will do exactly the same thing again. So when it comes to CD quality audio, it's actually sampled at 44,100 cycles per second, or hertz. Every second, it's grabbing 44,000 or so points. So this is the sampling frequency and the resolution we're going to use for our audio so that it sounds good. Okay, now a little bit about the frequencies we can hear. We just created a sine wave of 1 or 2 hertz, but we'd never be able to hear that because the human ear can only hear, if you have really good ears, you can hear from 20 hertz to 20 kilohertz, 20,000 hertz. And the thing we're modeling, the piano, has specific primary frequencies associated with each key. So there's 88 keys, and they vary in frequency response, or I should say in the frequencies that they exhibit, from 27 hertz on the lowest end to a little over 41, almost 4,200 hertz at the super high end. Okay. So we're going to find a good starting point at a note called A4 or A440. And I think they sometimes call this concert A, but it's sort of a central, it's the A that it's above middle C. And it's nice because it's a nice, doesn't have a fractional part. It's exactly 440 hertz. So let's try to produce this sound for 2 seconds. All right. Let's go in and try that. So we actually want sampling frequencies to be 44, 100. Oops, 100. I want Y to be, I want F to be equal to 440 hertz. And then I want Y, which is going to be the actual waveform, to be equal to, sorry, one more thing. Duration equal to 2. So this is now duration. So time is starting at 0. It goes at 1 over 44,100 up to 2 seconds. Okay. Now I'm going to make Y equal to the sine of F, which we just defined as 440. Convert to radians, per second, 2 pi, times t, which is our time vector. Okay. Now let's plot that real quick. T by y. Okay. There's a lot of cycles in there, right? Let's zoom in just a little bit. Okay. We got good stuff going on here. Alright. So let's use our sound command y fs and hit go. Okay. That was pretty good. So now we'll close this figure. I'm going to play that one more time, see if you can catch something. One more time. Okay, I don't know if you'll be able to hear it in the recording. Hopefully we'll be able to hear it in session. But there's kind of a... Okay, so this is what we just did. And we added some other labels and things. Okay, I want to ask, what's with the clicks? There are clicks in the sound. And it's kind of difficult to separate them out from the frequencies, because it almost sounds like the hardware is engaging or something. But I'll copy this and put this in another script, and you'll be able to hear what I'm talking about. Okay. So that took about 2 seconds, about 88,000 samples, and we're sampling. So what I did here was I just made a step. In fact, I can plot this. Do it down here so I don't have to run it again. Plot my step. And if I pan around a little bit, I just went up to 1 and back down after 90,000 samples. Okay, so that's kind of what's happening if you think about the waveform, because it's starting up so fast. Our ear hears something very abrupt, and it might actually be ending very, very fast. So we need to kind of smooth this out. So if I play this one more time, whoops, I don't want to save it. I can hear those clicks. Basically, we need to ramp into this and ramp out of it. That's what we need to do. Alright, so this is a problem. We don't want to have that ramp up and ramp down so quick. And if we look back at our test signal, that's kind of what it does. Ramps up and down really, really quickly. So let's add an envelope for the attack. So you can think about it, instead of it going all the way up to 1 really fast, staying that way and then coming back down, we want to add something that lets it ramp up and then ramp back down again. So a nice way to do this is with the sine wave, and we just need half of the sine wave. We don't need the lower part of the half. We don't need the second half. So all we have to do is figure out how to scale this so that it matches the duration, so that the frequency of the envelope is basically half the time period of the envelope is about twice as long as the duration, so that we only get half of the envelope to scale. So this will make more sense when we actually do it. So let's go and do it. So how do we go about doing this? Well, first we've got to figure out what that duration is. So we need to kind of rough out our the envelope parameters. So let's go do that real quick. Back to MATLAB. Start another one. We'll call this one clear format compact CLC. Save it as test2. Playing with the envelope. Alright, so we need to do the same thing. We need to say fs equals 44100 ts, time of the sample, is 1 over fs. We need to create, we have a duration of, let's just call it 2. And we'll make it 1 for the moment. And then we'll create the time vector. So the time vector will be 0 steps of sample time all the way up to duration. Excuse me. And then we'll take and create an envelope equal to sine of t. Okay. So if we leave it just as it is, so this will give us the same sampling rate as we have the other thing, and it'll give us the right number of points. But let's plot the envelope real quickly. T by the envelope, and see if see, this is still only, this is 1 radian. So that's one thing we need to change. We need to say 2 times pi times t. Okay. So there's 2 pi radians over one cycle. Okay. But we really want a envelope frequency. We'll call it EF. And this should be equal to something. Let's just say it's 1 for the moment. So we're going to put EF in here. Hit run and it'll do the same thing. We need to say for any duration, this is only going to finish half a cycle. So we know that for 1, it's going to be 0.5, right? Because 1 cycle per second, we only want this to do half a cycle. So if you follow my reasoning here, I can say we can take the duration, maybe it's 3 seconds, and just divide by 2. Okay, now if I hit go, sure enough, it gives me just the top half, and it ends exactly at 1. That's where I want it to be. If I had a 3-second duration and hit go, well, we didn't do do this right? What did I miss? Oh, we need to actually do 1 over the duration. Sorry, my fault there. And then divide that by 2. So if the duration is 3, in other words, if we have a very long duration, then we need a slower frequency. So once this gets bigger, this needs to get smaller. So we'll do 1 over duration. So what I'm doing here is just testing to make sure that as I change the duration, that the envelope stretches with it. Okay? Looks like that's working great. Awesome. Okay, so now we need to combine this thing. So like we had 1 over duration times 0.5, we already have all this stuff. So we just finished that part. Alright. So the next thing we need to do is combine them. What do I mean by that? I mean, we need to combine the envelope and the sound part. So I'm going to create a new one, new script. I'm going to call it test3. Okay, I'm going to take all the good stuff we have here. Good. Put it in. And then the new stuff we have here, I'm going to put it in just above. Okay. So I'm going to put some comments in here. Here are the parameters. Here's the time vector. Our primary frequency. Our envelope frequency. This is the envelope itself. Okay. Here is the sound bite, sound wave, or note. Okay. So basically what we want to do to combine them is multiply them together, right? So let's just stick E and V in front of this, say multiply by, and give it a shot. It says, inner matrix dimensions must agree. What the heck? Okay, so let's think about this for just a moment. We have this env variable, which is a vector, right? That's the same length as t, and we're creating a new vector, y, but we're multiplying the sign of this t times, so this is a vector, multiplying it by another vector. And like I mentioned in the beginning, this is our first foray into higher dimensional spaces. So we're not in super high dimensions, we're just in one dimension. But things are starting to change a little bit. So it's basically saying that the two variables are not compatible to be multiplied this way. And what, I'll not go into too much detail here, but just to say that when you multiply straight, like this, it implies a vector or a matrix multiplication, or sometimes called the cross product. And to perform the cross product, you actually have to, since there's two sizes, so we can say size of E and V and size of T. Okay, So they have the dimension 1 by 88,201 and 1 by 88,201. So when you multiply them together, you have 1 comma, or you could think of it this way, that the sizes are like this, times, and what it's telling us here is if you want to multiply, then these two have to agree. They have to be the same size, which they're not. And you can say, oh, well, that's all right. I just need to spin these around and say, E and V equals, here's a quick thing, we'll use the transpose. Now I'll just say E and V is 88,201 by 1, and then that'll match the 1 over here. Okay, so let's just make a test variable just to see if this works. So I'll call it test var equals env times t. And it says request would require 58 gigs of memory. Array exceeds maximum size preference. Creation of arrays bigger than this, blah, blah, blah. Okay, well, let me give you a hint of what we would have done. This was trying to create a matrix that was 88,000 rows long and 88,000 columns wide, which would have taken 58 gigs, which I don't have on this little laptop. So okay, something is weird here. I know a vector is one-dimensional. I know a matrix is two-dimensional, 88,000 by 88,000. What just happened here? Well, maybe what I should do is take t and multiply by e and v. Maybe that makes sense. Okay. Well, this is weird. This gave us one number. So multiplying one way gave us something zero-dimensional in one order, and multiplying in another order gave us something that's two-dimensional. And why on earth can't we find something that's one-dimensional? You can think of this as what's going on in space and how those rows, how those vectors are being combined in a matrix way of thinking. And it's pretty interesting, actually, to think about the fact that actually the once you get out of zero dimensions and get into dimensionally higher spaces, like 1 and 2 and more, they don't necessarily stay. So if you multiply a scalar, zero dimension, times another scalar of zero dimension, it stays zero dimension. If you multiply a matrix with the right size times another matrix with the right size, if they're both, they're not vectors, the result will be a vector, the result will be a matrix. But vectors are kind of odd that they can actually, and this happens in higher dimensions too, but we actually can't hit what we want to here. So what do we need to do? Well, let's get back to the point here. We actually need to use the dot operator, and that's for element-wise multiplication. So I don't need to change E and V around. It can be 1 by 88,201, and T can be 1 by 88,201. I want for each element excuse me, hold on just one moment. So all we have to do for this, actually, why is this blinking? Sorry. All we have to do for this is to add the dot operator in front. Alright, so let's hit run here again. Now, here's a visualization of the sound wave. We can zoom in a little bit on this. I'll make it just a horizontal zoom. So it is a sound wave. It starts out small. It ends up small. has a nice envelope here. And hopefully you'll be able to hear this. There's no click or pop. Nice and smooth. Okay. And that was using the dot operator for element-wise multiplication. Alright. So yeah, there's in higher dimensions, there's matrix multiplication, there's scalar multiplication like dot product, and then for array operations, there's element-wise multiplication, and that's what we use the period or dot operator. This should actually read dot operator, not dot product. Okay, very good. Alright, so this is what we just did, and this applies to raising something to a power. It applies to dividing. You know, you can divide in an element-wise way. You can add, subtract, all those sorts of things. Although addition and subtraction are implied, because whether you're talking about vector math or array math, addition and subtraction have the same effect. But for these things, like raising to a power, dividing, multiplying, you need the dot operator to do things in an element-wise way. Okay, so if we go forward a step here, graphically, what we had was we're combining an attack envelope, different envelope. We're combining that with a sound vector by multiplying it, and that gives us a shaped sound vector or sound wave. And this way we don't have those same little clips in the beginning and clips in the end. Okay, great. But we said we wanted to adjust the attack, right? And right now all we have is a sine wave. So we want to think about this for just a quick second and think, how could we bend this? And the simplest way for our purposes is actually just to take the envelope and raise it to a power. Let me show you real quickly what I mean. So let's see. We'll put this in test 2. We don't need a new one. So here's our envelope. So p equals 1. Let's take this envelope. We're talking about the sine function here. So we'll raise it to a power. Again, it says if we're using the exponentiation operator, inputs must be a inputs must be a scalar and a square matrix. Otherwise, use power of element, dot and up arrow. So same kind of thing. We need to use this in an element-wise way. Okay. Actually, I meant to make that to the p, because we defined p here. Now watch as we shift p, how we can change the shape of this attack. And you could think of this as more of a staccato. It's a faster, it doesn't have the clip because we have a nice smooth ramp in, but it's a faster hit once it gets there, even though it's the same frequencies. And then on the other side, so we were at 1, we can actually go lower than 1, 0.9, and we can watch it bend out. So this is, have to be careful we don't go too far, otherwise we'll hear those clipping sounds again. But we can see how this is actually making it flex out. And why don't we do this? We'll say while p is less than 10, we'll start p at 0.1, Oops, I already had that there. Just so you can see this. Hold off. P equals P times 1.5. So we're going to increase P and say, hold on. So this gives you an idea of kind of how we can change the shape from 0.1 all the way up to just below 10. Okay, very good. So we've got 15 minutes left. Now, you might have noticed it's odd that this doesn't sound exactly like a piano yet. And that's because we're simplifying. Even though pianos actually generate more than one frequency, we're only generating the primary. So on the right-hand side, what this is a frequency transform, an FFT. Stands for the fast Fourier transform. And this shows you which frequencies are present in a signal. And we'll use this maybe at some point during the sessions, but for right now, what this is showing us is that the strongest signal, the highest magnitude frequency content, is right around 440. But then this isn't our signal, this is a piano. But you can see how there are harmonics, so integer multiples. So this is 1 times our primary, 2 times the primary, 3 times the primary. See how they're evenly spaced? So this structure is called the harmonic structure of the note, and you can create all kinds of crazy different sounds by creating sine waves that have different harmonic structures. So it actually is kind of a neat way to think about approaching sound design. If you're into audio, I'm kind of into audio, and I think it's kind of neat. But you can mathematically sculpt your sound, and it adds a different kind of aesthetic to what you're trying to do. So we're not going to worry about all these things. We're going to say, for the moment, this is good enough. There's also a lot of other effects to think about, how the decays, how things echo. There's echo chamber effects. There's obviously a lot that's going on physically inside of a piano, but for the moment, this is the sound we need. Okay, we're almost done here. So what's left to do? So we've accomplished most of the vector stuff. Basically, we can generate a tone at a particular frequency. We created a shaping envelope for the attack and combined them. So what's left to do? Well, now we've got a couple abstraction layers to build. We need to create a layer to translate the name of a key to a frequency, and we need to create an abstraction layer to sort of hide all the dirty details of production of the waveform and the duration and the envelope and the attack and all those things. Because we want to make it really easy. We want to write, like 1 note per line. So in order to write things efficiently. So we want to abstract ourselves and then create a nice interface. Okay, so how do we do those things? So here's the plan. The lowest level, we need to have a frequency note. When we press C4, we want a function that can tell us the frequency that C4 is. And then above that, we use the stuff we've already developed to generate a sound and duration attack, and that will actually send something to the sound card. And then at the highest level, we're going to write a song. So we'll do this at the end. This part's already done, and this is almost done. We have to put it in a function, and this is what we need to do right now. Okay, so a layer to find the note frequency. That's what we're working on. All right, a little bit of water here. Okay, so what we have at the right here is, I'll zoom zoom in here. We need to find a function that maps these things. So all we really have, we need to send it a string like C3, D3, E3, F3, so on, and we need to hand it back a number. Pretty straightforward, actually. So I am going to switch to MATLAB, and I'll leave that as it is. And I'm going to write a function called find frequency, or FF to be simple. And it's going to take, well, it's going to return a frequency, and it's going to take in a note. Okay, so I'm going to use the switch keyword, and I'm going to switch note, and in the case that the note is C3, then freq equals 130.81. In the case that it is D3, frequency equals 146.83. Case E3, frequency equals 164.81. Case that it is F3, we're just going to skip the black ones because just so that this doesn't take quite so long, we'll just write it where we don't need any of the black keys. 174.61. Case G3, I'm going to not capitalize so I can type faster. 196, well, that's even, that's kind of nice. Case A3, frequency equals 220. Case B3, frequency equals 246.94. Case C4, frequency equals 261.63. Case D4, frequency equals D4 293.66. Case E4, frequency equals 329.63. By the way, I got this online. You can go look this stuff up. It's not secret. You can even generate it with a formula, but it's useful for us to do it this way. Okay, E4, F4, frequency equals 349.23. Case G4, so equals 392. Case A4, frequency equals 440. Case B4, frequency equals 493.88. Case C5, frequency equals 523.25. Case D5, frequency, it's kind of boring, but we just need it for our project, and I want to do it with you. Case E5, frequency is 659.25. Case EF 5, frequency is equal to 6 F5 698.46 case G5 frequency equals 783.99 case A5 frequency equals 880 case B5 frequency equals 987.77 case C6 frequency equals 1046.5. Otherwise, frequency is equal to, let's do something kind of low. So 130, let's do it like 80 hertz or so. And that's it. That's all we need to do. All this has to do is find the frequency of a note. So I'm going to save this. And I'll save it as FF. Hit save there. Okay. Now we're getting low on time, so we've already done, so that's the lowest layer. So now we're going to write a function called play key, or PK. And we don't have any return arguments. But we want to pass in a note, a duration, and did I already add something called play key? Oh, okay. I'm going to call it PK2. I think there's a PK2 also. Make it PK3. So I'm going to add in a power for the attack duration, the power of the attack. Okay, so we'll use our test 3. It has all this stuff. We'll copy and paste this in. Okay. Sampling frequency, sampling time, duration. Okay, we don't need to define duration because that's getting passed to us. Okay, here's the time. Now F will now be equal to find the frequency of the note. Okay. And what else? Okay. We need to put a semicolon so we don't see that. Okay, this is our envelope frequency, the envelope itself. But we need to change this envelope to be raised to the sign, to the power of P. So sign to the P, which I think uses note, duration, and P. Okay, we've used everything. And this will plot T and Y and give us a sound. So let's save this. PK3. Alright. Clear. Format compact. I call this play notes. PK3. Let's try something we know. A4, 2 seconds, attack exponent 1. Not too bad, not too bad. Okay, let's PK3 how about C5 to 1. PK3 E5 to 1. So what's going on? I thought this would play one and then the next and then the next, right? Well, actually, what's happening is it's running through and doing these in sequence, but it's sending to the sound card and then returning. So the actual playing of the sound takes time, but it doesn't take much time to send it to the sound card. So from the point of view of play notes, these are basically happening at the same time. So in this way we can play a chord if we wanted to. But why don't we do this? Why don't we say, we'll do Mary Had a Little Lamb. That one's not. Or how about the first few bars of Star Spangled Banner? So that goes, oh, say, can you see? So it starts with G. If we play this in the key of C, I have to take my word for it, but you could look it up. So if this goes, oh, say, G4. And I'm going to also so there's going to be a bass time, which I'll make 1 second, and we'll just put this up so we can change how these sound a little bit quicker. So quarter note is bass divided by 4, half note is bass divided by 2, a whole note equals bass. So I'm going to use a quarter note here, and I'll set the attack. Attack power equal to 1 at first. Maybe I'll call this AP so it's not so long. Okay. So now I actually need to pause because they end up going there at the same speed. So I'll pause for a quarter note, quarter time. And then I'll PK3, oh, say, so it goes G, E, C, E4, quarter note, attack power, pause for a quarter note while that's playing, PK3, oh, say, C4. But actually this one gets held a little bit longer. If you think about the song, it goes bum, 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 bum. So, dun, dun, dun. Maybe we'll make this a half note. AP. Pause for a half note. Let that play. And then go back up. PK3, E4, quarter note, attack power. Pause for a quarter note. Dun, 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 dun. So we go back up to G. Pause for a quarter note. PK3. Aren't we glad we abstracted these things and made a nice interface? Otherwise, we would have just written a couple pages of code right here. So this goes dun, 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 dun. So that goes up to C5, and I think that's a whole note. Now let's just try this to see if this sounds right. Let's hear that again. We'll turn it up a little bit. Hopefully you can hear better. Dun, dun, dun. So I'm going to make this a half note. And this is a half note. dun, dun. Maybe this should be a whole note too. And this should probably be a half note. Half note. Whole note. Not too bad. And you can see how it goes from here. So I think we'll stop there. Oh, well, we have to play just a little bit with parameters, right? So maybe we want to, I was going to stop here, but maybe we want to play this a little bit slower. We could make the bass time a little bit longer. That's kind of cool. Maybe we want it a little more staccato, so we could change the attack power. So lots of interesting things. But I think we have a pretty good model of a piano, and we could start to write some interesting songs here if we wanted, and even start to combine different attacks. I think if you wanted to challenge yourself, figure out how to write a vector of keys to feed into this. Maybe there's a pattern that you could start rounding, you know, like a sine wave of keystrokes or something like that. I think there's some interesting places you could go with this, but I better stop here because we're past our 2-hour mark. But thanks for joining me, and I hope you enjoyed it and learned a lot. And yeah, have a great rest of the day.